All right, let's dive right in. This isn't going to be some boring textbook lecture. Nope. This is a real, hands-on guide built for the shop floor for you, the people who get it done shift after shift. We are going to turn you into a full-blown defect detective.
Look, our mission, it's simple. 0 defects. And I'm going to tell you right now, the most important person in hitting that goal is you, the operator. You've got the eyes, you've got the hands, and you have that gut feeling to spot trouble before it even starts. You're the front line of quality, so let's get you the tools you need to win that fight.
First up, we're going deep inside the casting. We're talking about the defects you can't see from the outside, the hidden flaws that are absolutely critical to the strength of that final part. The investigation begins now. Okay, our first suspect is called shrinkage porosity. Just look at that description. Jagged, irregular, almost like a little crystal cave grew inside the metal. You're going to find this sucker hiding out in the thickest sections of the part, or in hot spots where heat just can't get out. It's a dead giveaway that the metal was starving for more liquid as it was trying to solidify.
So what causes this starvation? Well, it boils down to a few key culprits: poor solidification paths, risers that are too small, and those pesky hot spots. But really, it's all about one thing: shrinkage. As aluminum cools, it shrinks by about 6 to 8%. That's a lot. And if the thickest parts get cut off from a supply of fresh liquid metal while that's happening, they literally starve. And bam, you get these voids.
So how do we stop this from happening? We've got a 4-part game plan. First, we take control of the cooling. We use things like metal chills to pull heat out faster from those chunky sections. Second, we make damn sure our risers are the absolute last thing to freeze, so they can keep feeding the part. Third, a slower, more controlled pour usually helps. And finally, you gotta have smart gating. No sharp turns that create those hot spots and choke off the flow.
Okay, next on the list, gas porosity. Now, unlike the jagged look of shrinkage, this defect shows up as perfectly round, smooth-walled bubbles. Just think of it as trapped gas. You'll usually find these little guys clustered near the top of the casting like they were trying to escape, but got frozen in place.
So, where's all this gas coming from? Well, sometimes it's just air that gets churned into the metal during a messy, turbulent pour. But the real big one? Hydrogen. It can come from even a tiny bit of moisture or grease on your tools or the ingots themselves. And if that gas has nowhere to go because the vents are blocked or just not there, guess what? It's trapped for good. The solution here is a 3-pronged attack. Number 1, pour it smooth. Use those tilting pours to get a nice, calm, laminar flow. 2, give the gas an escape route. That means better venting in your mold and in your cores. And 3, and this is probably the most important, clean the metal before you even think about pouring. Proper degassing and fluxing gets that nasty hydrogen out before it ever has a chance to ruin your part.
Our last internal bad guy is inclusions. You can think of this as just contamination. It's unwanted junk, oxides, slag, maybe even sand, getting trapped inside your otherwise perfect metal. They'll show up as these dark, flaky spots or weird films inside the part, and they create major weak points.
Now here's what's so interesting. Notice a theme here. Look at that first point, turbulent pouring. It's our repeat offender. Just like with gas porosity, when you pour like you're putting out a fire, you fold that ugly oxide skin from the surface right into the mix. You combine that with a dirty melt or some sand breaking off a core, and you've got yourself a recipe for disaster.
And this is exactly why the fundamentals are so critical. Once again, a smooth laminar fill is your absolute best friend. But you can also be proactive, right? Use ceramic foam filters in your running system. They literally strain out the impurities. And be relentless about your cleaning and skimming practices. Keep that melt clean from the very, very start. All right, team, let's move out from the inside of the casting and head to the surface. These are the defects you can see with your own 2 eyes. They're the ones that tell you the story of how that metal flowed, or, more importantly, how it failed to flow into the mold.
First up, we've got the cold shut, or its ugly cousin, the misrun. This one is super obvious. You'll see a clear line, a seam, where 2 fronts of molten metal met, but they were just too cold to properly fuse together. A misrun is even worse. That's when the metal literally gave up and solidified before it even finished filling the mold.
So what's the deal here? It's all about temperature and speed. Simple as that. Either the metal is too cold when you start, or you're pouring it too slow, which lets it freeze up before it can do its job. And of course, bad gating that slows down the flow is a huge problem because it just makes the metal lose heat even faster.
So, the fix? We crank up the heat and the speed. Keep that aluminum melt in the sweet spot, generally above 650 Celsius. Pour fast enough to get that cavity filled up quick. And here's a great pro tip. Using a coarser mold coating, like die coat, can act like a little thermal blanket, keeping the metal hotter for longer as it flows.
Next up, we have hot tears. These are nasty cracks that form while the casting is still hot and really, really weak. It's literally tearing itself apart as it cools down and shrinks. You'll almost always find these things at stress points, like right where a thin wall suddenly meets a big, thick section.
So why does it tear? Okay, imagine you're pulling a piece of hot taffy. When it's super soft, it can stretch, but as it starts to cool, it gets brittle, and it'll just snap if you pull too hard. It's the exact same thing here. Your solid steel die is rigid. As the casting tries to shrink, the die holds it in place, building up a ton of stress. And those sharp internal corners? They're like a dotted line telling the tear exactly where to start.
Preventing hot tears is all about relieving that stress. You can change the mold design to get cores out of there sooner. You can even play with the die temperature or use insulating coatings to slow down the cooling in those high-stress zones. But the most fundamental rule? Generous fillets and radii. Get rid of those sharp corners.
Okay, we've been tackling individual defects one by one, but now let's zoom out. Let's talk about the big picture principles, the toolkit you can use to prevent a whole bunch of defects at the same time. You master these and you are well on your way to that zero defect goal.
If there is one golden rule in all of casting, this is it. Just look at the two sides here. On the right, you've got turbulent flow, that chaotic, messy pour. It whips air into the metal, giving you gas porosity, and it folds in all that surface gunk, leading to inclusions. But on the left, laminar flow. Smooth, calm, controlled. It's the key to preventing both of those problems with one simple action. Every single pour should look like that.
Now this is really cool. Take a look at this graph. It shows us everything about consistency. See how for the first, say, 30 or 40 cycles, the process is all over the map while the die heats up, but then it settles down, it finds a rhythm, it gets stable and predictable. Your job as an operator is to get your process into that stable window as fast as possible, and then keep it there. That's where you make perfect, defect-free parts every single time.
We've covered a lot of technical stuff, but I want to end with the single most important tool in the entire foundry. And it's not a machine, it's not a computer, it's you. It's your eyes, your experience, and your attention to detail. I want you to let this one sink in. Cleaning is inspection. Seriously, when you're cleaning your die or your tools or your furnace, you're not just tidying up. You are performing the single most critical inspection of the entire day. You're looking for wear, for buildup, for anything that seems out of place that could cause a defect on the very next shot. It's the definition of proactive defect prevention.
So I'm going to leave you with this one question. Based on everything we just went over, I want you to think about it right now. What is one specific thing, one small change, or one thing you can pay closer attention to that you can do on your very next shift to get us all one step closer to that goal of zero defects? That's how we make it happen. Thank you.